Welcome back to Maths with Mrs. J. It's time for another algebra challenge. And this one's kind of cool because it involves both a recursive function and a composite function. Just to remind you, a composite function means a function of a function, and a recursive function means one where each subsequent function is defined in terms of the previous one. In this case, the recursive definition is a composite function. Our task is to find f 2020 of x. 2020 has not been the best year, but I'm pretty sure we can come up with a good expression for f 2020, and we might even be able to come up with a general solution here for fn of x that doesn't have to involve recursion. All right. Now, we're told that f1 of x is x over x plus 1, and we're told that fn plus 1 of x is f1 of fn of x. Probably the best way to start here would be to start finding f2 and f3 and see if we're starting to build up some sort of pattern. So f2, using our recursive definition, will be f1 of f1, because in this case n is 1. So f of 2, n is 1, so it'll be f1 of f1. So it's f1 of x on x plus 1. This means in our f1 rule, wherever we see an x, we're actually going to put x over x plus 1. So in our numerator, we're going to have x on x plus 1. In our denominator, we'll have x on x plus 1 plus 1. Tidying up a little bit, in our numerator, we'll be left with x on x plus 1. In our denominator, I want to put everything over x plus 1. So we'll need x plus 1 on x plus 1. Now, because of the nature of working with rational expressions, if you're dividing by a rational expression, that's the same as multiplying by the reciprocal. So these x plus 1s are going to cancel, and you're going to be left with x on 2x plus 1. Okay, let's find an expression for f3 of x. So f3 of x will be f1 of f2 of x, using our recursive definition. So it's f1 of this expression here that we found. So x on 2x plus 1. So wherever we see an x here, we're going to put x over 2x plus 1. So x over 2x plus 1 over x over 2x plus 1 plus 1. Again, I want to tidy up that denominator. Put it all over 2x plus 1, and we're left with x plus 2x plus 1 all over 2x plus 1. Same thing's going to happen as happened here. These 2x plus 1s will cancel, and we're left with x over 3x plus 1. Now let's just have a bit of a look at what we've found so far. f3 of x is x over 3x plus 1. f2 of x is x over 2x plus 1. So I'm thinking that potentially fn of x could be x over nx plus 1. In which case, f 2020 x will be x over 20x plus 1. Now, before we can take that leap, we really need to sort of look into this a little bit more seriously. If you're trying to prove something by recursion, you need to prove that it holds for the first one, which it does. And you need to prove that if it holds for n, it will hold for n plus 1. Okay? So we're allowed to assume that this works. So we've already said it holds for n equals 1. That's all good. So now we're going to assume it holds for n is k, and use that, prove that it works for n equals k plus 1. Well, let's have a look. So we're going to assume that fk of x is x over kx plus 1. So fk plus 1x, using our recursive definition here, is f1 of fk of x. Now we're assuming that this holds for n as k. So it's f1 of x over kx plus 1. So we're going to sub this in here. So we're going to get x over kx plus 1 all over x over kx plus 1 plus 1. Tidy up our denominator, and we're going to get x plus kx plus 1 all over kx plus 1, running out of room, sorry. So we're going to end up with x over x plus kx is k plus 1 times x. So we've actually proved that now. So we said it held for n equals 1. We've assumed that it works for n equals k, and that has actually shown us that it works for n equals k plus 1. So we're now all good to say that yes, that rule works, and therefore f 2020 of x is x over 2020 x plus 1. And there you have it.